Hi guys, hope you are doing well. And yesterday's video was a bit smaller video, just discussing four definitions, and especially root mean square velocity, and mean free path. Today we are about to discuss about the pressure of an ideal gas. This is one of the very important equations in kinetic theory of gases. So we are going to see the derivation. So many boards ask this derivation in their exams. However, we also utilize this final formula for pressure in many of the MCQ type of questions. So let's begin. The derivation is kind of long, and maybe today's video is going to be long too. Now, we are going to consider a box, and this enclosed box is in a form of a cube, and there are lots of molecules in the box, but we are going to focus on one single molecule, and this molecule has some velocity, let's say c1. Because it's the first molecule, I am calling it as c1, and this velocity c1 is having three components, that is x component, the y component, and the z component. So I am denoting x component as u1, the y component as v1, and the z component as w1. So these are my components, u1, v1 and w1 are my components of x, y and z. I am assuming that the L is the side of the cube. So if I wish to find out the area of this face, then it would be L square, and if I wish to find out the volume of the cube, it would be L cube. So this is all what things are we are going to utilize in the derivation. So I just written what we are considering and what terms and terminologies we'll be using in the entire derivation. So consider a gas enclosed in a cubical container. It should be a cubical container, and later on we'll realize that it doesn't matter if it is a cube, even if it is a cylinder or a cone or a sphere, the formula still holds good. Now I am assuming that small m be the mass of a single molecule and n be the number of molecules present inside the container. So m is the mass of the molecule, and there are lots of molecules, and I'll call this as n. So mass of the gas becomes m, which is number of molecules into mass of a single molecule. So if I multiply mass into the number of molecules, I'll get the mass of the gas. L with the side, I have already mentioned, L square is the area, L cube is the volume, and density is written as rho. So the sign is called as rho, and it's written something like this. And density ka formula is mass upon volume. So mass is Nm and volume is L cube with the density. C1, C2, C3 are the velocities that I have mentioned already. U1, U2 are the x components, V1, V2 are the y components, and W1, W2 with the z components. So this is all we are going to utilize in the entire derivation. So let's see going forward. Now what I'm going to do is, we are going to find out the velocities first, because this is going to be needed at the later stage of the derivation. So if you have done vectors, you might have understood if I have a resultant vector r, if I want to find out the magnitude of r, it is nothing but r is equal to root of rx square plus ry square plus rz square. So you see, it's just the x component ka square, y component square, and the z component square, and if you take this root on the other side, this becomes r square equal to rx square plus ry square plus rz square. So if c is my resultant velocity, u1 is my x component, y component, and the z component, then using this equation, I can write as c1 square is equal to u1 plus u1 square plus v1 square plus w1 square. Same it will hold for 2, and same it will hold for the nth particle. So this thing I am going to utilize at the end. Let's go ahead. Now this is a procedural derivation. So what we have initially did was, we have already found out velocities. Now we are going for the momentum. So if you observe here, the initial momentum of the molecule, I am assuming that the molecule is just moving in the x direction. Had that molecule moving in any random direction, it would having x, y and z component. But if the molecule was just moving in the x direction, its entire velocity would have been u1 and the mass is m1. And momentum ka basic formula is mass into velocity. So mass is m and the velocity is u1. So the momentum is mu1. So initial momentum of the molecule is mu1. Now what happens after that? This molecule collides with this wall, the wall PQRS, and it rebounds. It goes back. So while going, its momentum was mu1. While returning, its momentum would be minus mu1. And the reason is it has changed the direction. It's just moving in the opposite direction. So the final momentum is minus mu1. If you are observing here, minus mu1, and this was plus mu1. Then change in momentum of the molecule will be final change in momentum is final momentum minus initial momentum. So minus mu1 minus mu1. This is final, this is initial. This is final and this is initial. So I'll get minus 2 mu1, and this is the momentum of the molecule. Now if this much is the momentum given by the molecule, then this is the same amount of momentum which will be gained by the walls of the container. So change in momentum of the wall is 2 mu1, that is the plus sign, because the molecule is going to give its momentum to the wall. Okay. Then comes speed is equal to distance upon time. So speed is u1, now time is t, and distance. Now how come we found out the distance? Now a molecule, when it collides to this wall, let's say it collides PQRS, and then it again collides this wall PQRS after it has traveled on the other side and it has changed direction and come back again. While this entire thing was happening, it has traveled a distance of L plus L, while going L, while returning L, that is 2 times L. That's why we take 2L over here. So the distance traveled is 2L and time is t. So I just move this thing here, t goes this side and u1 comes here. So t is equal to 2L by u1. I have named this equation as 1 and named this equation as 2. Now the one more question arises, like why we are doing it like this? Because we know that we are supposed to derive pressure. Pressure is force upon area, and in order to find out force, we are using Newton's second law, that is change in momentum with respect to time. So in order to find out pressure, you need force, and in order to find out force, you need change in momentum as well as change in time. So I have found out change in momentum and I have found out time. So I will get force. Let's do it. So force is equal to dp by dt. In place of dp, that is the change in momentum, I'll put it over here, 2mu1, and t as dt, that is the change in time. So what I get is mu1, 2 and 2 gets cancelled, u goes up, so I'll get mu1 square upon L. Now if this is done for the first particle, then for the second particle you just have to place 1, in place of 1 you can just place as 2, so this becomes 2. So I get F2 is equal to mu2 square upon L, and same way for n I let Fn is equal to mun square by L. This is just an extrapolation. Now if all these molecules are striking the wall PQRS, then the total force exerted on the wall would be the addition of all these forces. So total force in the x direction would be Fx, which is the addition of everything, F1 plus F2 3 till Fn. Now if you observe in Fn, in F2 and in F3 or Fn, you will find out m upon L is common. So I have taken m upon L common. What remains inside is u1 square, u2 square and un square. So I hope you are following at this point. Now also pressure is equal to force upon area. So right now we are coming to the last and final steps. So pressure is force upon area. Now pressure on the wall X is equal to force on X upon the area of X. Now just observe this. I have just clubbed few steps as the derivation is pretty long, and I can just club a few steps. Even if you want to club few steps and you find out some steps easier, then you can just club it and make the derivation shorter. So fx is this fx is this term, area is L square. So if you see, there is an L here and there is an L square term here in area. So L square and L will become L cube. So this becomes L cube. And if you see, m is as it is, this bracketed term is as it is. Now same, I can assume that if the molecule was moving in the y direction, my pressure ka term would have looked like this: Py equal to Fy upon A, m upon L cube. In place of u, which was the x component, now it becomes the y component, that is V. So V1, V2 till Vn. And same I can do it for z. So Fz upon A, m upon L cube as it is. And in place of x component, y component, now we have z component, which is W1, W2 till Wn. Now, in fluid mechanics, you might have learned about Pascal's law, which says that if you apply pressure in an enclosed fluid, then the pressure is transmitted undiminished throughout the fluid. So I can say pressure on the wall X, pressure on the wall Y, and pressure on the wall Z. These three are equal. This is what is called as the Pascal's law. Now because these three are equal, I am just assuming a single letter for all of them. So let's say Px is equal to P, Py is equal to P, and Pz is also equal to P. I am assuming that, I am saying that. So if I want to find out the total pressure, that is P, what I'll do is I'll add them and then we'll see how it works. So I have just added Px, x component, y component, and z component, which is equal to, now I'll put in the values of Px, Py, and Pz. So if you see, Px this term, Py this term, and Pz this term. So m upon L cube is common in each and every term. So I have taken m upon L cube common outside. And u1, u2 till un, v1, v2, vn, and w1, w2, wn. I am supposed to write that in a bracket, but I am just manipulating it. I am just writing all the ones together, 1, 1, 1, all the twos together, and all the n's together. So I get un, vn, wn. Now when I am writing this, I just see that I have already found out the value of u1 square plus v1 square plus w1 square as c1 square, and so it goes for c2 square, and so it goes for cn square. So I can just replace this from that part. So u1 v1 w1 becomes c1, u2 v2 w2 becomes c2, and un vn wn becomes cn. M upon L cube as it is, and this is P plus P plus P, which gives me 3P. Now, in order to find out pressure, I should get a quantity, I should get a formula in which I have some measurable quantities. Now C1, if I have a formula in terms of C1, C2, C3 till Cn, velocities of molecules, of individual molecules, you won't be able to find out. So we need to replace this bracketed term. So in the previous video, you might have understood, if you have gone through those videos. If you haven't, then just go back to the previous video. I have also created a playlist for kinetic theory. You can just see all the videos in a particular order. In that, I have mentioned that CRMS is equal to the square root of C1 square plus C2 square till Cn square divided by n. What I'll do is I'll take the square root on the other side, so this becomes square, and this n was divided, now it is going to get multiplied. So I'll get n CRMS square is equal to C1 plus C2 plus C3 till Cn. So wherever there is C1, C2, C3 till Cn, I can write n CRMS square. So I'll just put this value over here. So this C1 plus C2 till Cn square becomes equal to NCRMS square. So if you see, this is NCRMS square. L cube is nothing but volume. Now we are coming to the final step. N, that is the number of molecules into mass of a single molecule, gives me the mass of gas. So this is the mass of gas, that is capital M, CRMS as it is, V as it is. This 3 in the next step I am going to bring it over here. So 3 goes in the denominator, mass upon volume becomes the density, and this is the final formula for pressure of an ideal gas. So the boards which do not demand derivation, they can just remember the formulas, but there are plenty of boards in India who demand for the derivation part, how to derive that formula. Then in that case you can just go through this entire video again and again, and just write it somewhere. And also I would like to mention it, in the final formula, if you see, there is a mention of density and the CRMS. Now density is something which is like, it does not depend upon the shape of the container. So had we taken a cylinder, the formula would have remained the same. If we taken a cone, the formula would have remained the same. Taking a cube is just a matter where cube makes our calculation easier. That's one thing. Secondly, you will say, okay sir, if we want to find out pressure, then we need to find out CRMS, and how are we going to measure the CRMS? Now in the coming videos you will find out that in order to find out CRMS, you just need to find what is the temperature, and in order to find out temperature you just need a thermometer. So a thermometer will get me CRMS, and CRMS, if I put it over here, I'll get what the pressure of the gas is. Now there is one more question which people can ask, that sir, PV is equal to nRT, this is an ideal gas equation, and if I have this value, then why to do it with this? So if you see, PV is equal to nRT is a equation in which you connect with the external parameters like pressure, volume, temperature. These are the external parameters. But it was the first time when kinetic theory of gases got into consideration, that the pressure, that is the external parameter, got connected to the internal parameter, that is the velocity of molecules. So that's where the benefit of kinetic theory of gases comes in. So yes, a pretty long video, but make sure that you follow it well. If you haven't yet subscribed, then please subscribe the channel. And if you have any doubts and difficulties, then please comment. I would like to know what things you are liking and you are not able to understand, so that I can just modify my teachings according to what my audience is. Thank you so much.